Hello everyone, CK here. In this video we are going to learn vector analysis and basics of coordinate system, namely Cartesian coordinate systems, cylindrical coordinate systems and spherical coordinate system, and their interrelations and transformation from one coordinate system to another coordinate system. This is very much vital for understanding the theory of electromagnetics. What is electromagnetic theory? A study of effect of electric charge at rest or in motion. Static charge produces electric field. Moving charge or steady current produce magnetic field. And a time varying current or pulsating charges like in dipoles produces electromagnetic field. A field is a special distribution of a physical quantity which may or may not be a function of time. For example, electric field, magnetic field, like that. A time varying electric field is accompanied by a magnetic field and vice versa. That is, time varying electric and magnetic fields are coupled. You cannot have isolated time varying magnetic field or time varying electric field. That means if time varying electric field is there, you must have a time varying magnetic field, and we call that electromagnetic field. That is the basis of wireless communications. Study of electromagnetic theory is vital to understand cathode ray oscilloscopes, radar, satellite communications, wireless communications, microwave devices, electronics devices, injection laser diodes, and many more. Before moving into the coordinate systems, we will do little analysis about the vectors. We are considering vectors, so scalar comes into picture. What is scalar? At a given time and position, a scalar is completely specified by its value only. Current is a scalar, voltage scalar, like 5 ampere current, 4 ampere current, or in phasor notation 5 plus J3 volt or 3 minus J2 volt, like that. So these things or these scalars are specified by their values. Vector, and vector is specified by both its magnitude and direction. For example, electric field, magnetic field, you have a values and the directions. Now question is how we can define or represent the directions. That is taken care by coordinate system. Now we'll go to the vector. A vector A can be written as, let us say we want to represent a vector. So vector is represented as this arrow. This is the representation of a vector, is equal to a magnitude. Okay, this is a scalar and a unit direction, or you can say unit vector along this vector. V is equal to magnitude of a vector, and an is equal to, it is a dimensionless unit vector. with unit magnitude. So in the direction of A. I can write that unit vector an as the vector A upon P, or vector A magnitude of vector A. So graphically we can represent, this is your arrow, this represents the vector A, and from this to this tip to tell this distance is your magnitude, and this is your unit vector an. I have told you, dimensionless unit vector with unit magnitude. Magnitude is unit in the direction of vector A. So in short, I can write vector A is equal to magnitude of A into an. In Cartesian coordinate systems, vectors can be represented as scalar ax along the x-axis plus ay along ay plus az along the az. That means this is the magnitude along x-axis ax, this is the magnitude ay along the ay, and this is the magnitude along az. Vector algebra, addition, subtractions, then we'll go for the multiplication like dot product, cross product. If this is your vector A, this is your vector V, then this vectors becomes A plus B using the triangle law of vector. So we connect here in the same direction, same length, and this is your A. So A plus B becomes this vector. How to find the A minus B? Let this is your A, this is your B, so this is your V. So this vector in the red color becomes A plus B, right? Now how to draw a negative vector? As you know that vector, a positive vector, if it is a, what will be the minus A? Because magnitude remains same, direction is the opposite to the what was the vector A. So this becomes your minus A. So same way if it is B, so this will be the, in the yellow line becomes the minus B. So A, and this is your minus B. So this vector will be the A minus B. Multiplication of a scalar into vector. Suppose we have a vector A. I want to have another vector P, which is a scalar multiplied by A. So you see that it only changed the values, that is K, magnitude of A and an. That's all. Vector addition is commutative, that is A plus B is equal to vector V plus vector A. We called it commutative. Vector addition is associative. And vector addition is distributive over a scalar. Like K is a scalar, A plus B is equal to K A plus k. In Cartesian coordinate system, if A equal to so A plus B, so you need to add the corresponding scalars of these vectors like ax plus bx ax Now we'll move to the position vector. Position vector is the vector from origin to a given point. Given position in space. In Cartesian coordinate systems, I can write, let's say this is a point P, X, Y, Z. So position vector is the vector from origin to the point or position. So this is the position vectors OP. So I'll write OP position vectors in the Cartesian coordinate system as the x ax plus y ay plus z az. If you have two position vectors, let's say another position vector, let's say you have q, so this is the OP. Similarly, you can find the, let's say, unknown one, x1, y1 and z1. So OQ will be x1 ax y1 ay z1 az. If you find the vector PQ, so vector PQ from P to Q, then position vector OQ minus position vector OP. Or if you find the vector QP, that is from Q to P, that is OP minus OQ, or which is same equal to minus of PQ. Now we'll move to the vector multiplication. First we'll discuss the scalar multiplication, or we call the dot product. When we have two vectors A and B and acute angle between them is the theta AB, then scalar product or dot product between the A and B is the magnitude of A, magnitude of B, and cos of angle between them, that is the acute angle between them. AX with the AX, how much you will get? Magnitude of AX 1, magnitude of AX, and cos of angle between them. So 1 into 1, and cos the angle between them is the 0, so 1, that is 1. So what is the dot product between the AX, that is the unit vector along X and unit vector along Y. The magnitude of AX, magnitude of AY, and cos of angle between them. So magnitude of AX 1, magnitude of AY 1, and cos of angle between them. X and Y has the angle of 90 degree, mutual perpendicular. So cos of 90 is 0, so 0. So in the Cartesian coordinate systems, you can find the A dot B and dot product is commutative. A dot B is same as B dot A. Dot product is distributive also. A dot B plus C is equal to A dot B plus A dot C. Now we'll move to the cross product or vector product. So A cross V is the magnitude of A, magnitude of V, then sine theta AB, that is the acute angle between them, sine of that, then AN. AN is the unit vector normal to the plane containing vector A and B. Here is the, let's say this is your A and this is your B and this is your theta AB. So this will be the AN. So that is determined by the, when you do the A cross B, that is determined by the right hand rule. Can you see? This is the vector U, this is the vector V, and this is the vector U cross V. When you curl your fingers from U to V, the direction of the resultant vector, that is the cross product vector U cross V, is in the direction of the thumb. That is, you see, this is perpendicular to the both the vector. Similarly, suppose you want to find the, as per this picture, this is your U, this is your V. Suppose you want to find the V cross U, that is V cross U. So see, same way you curl your right hand from V to U and check in which direction your thumb is pointing. So obviously this will be the V cross U vector. So we see that U cross V is equal to minus V cross U. In Cartesian coordinate systems, if A equal to then A cross B will be the in the form of determinant. We are doing the A cross B. First you write unit vector because it is a vector product, AX, AY, AZ. Then component of A, AX, AY, AZ. Then write BX, BY. What is the AX cross AX? Obviously 0, sine 0, 0. AX cross AX, AY cross AY, AZ cross AZ, all 0. And AX into AY will give you the AZ. How you determine? You determine with the help of right hand. So X, Y, Z, just write it X, Y, Z. That means X cross Y give you Z, Y cross Z, I mean AY cross AZ give you AX, then Z, AZ cross AX will give you the AY. If you do the reverse way, AX cross AZ give you the minus AY, like that, like AZ cross AY will give you the minus AX. So you can find all other a trivial cross product. So you can go and you can also practice with respect to a right hand coordinate system. X, Y and Z. You see, when I move X to Y to X, what happens? When I move X to, Y to X, then the cross product between them will be this direction, that is minus AZ. If I move from X to Y, curl my right hand fingers, that will be the AZ. Cross product is not commutative. A cross B is not equal to B cross A. In fact, A cross B is equal to minus of B cross A. It is not associative, but it is distributive. That is, A cross B plus C is equal to A cross B plus A cross C. It is distributive. And you know, a vector crossed with the same vector 0 and a vector dot with the same vector A magnitude square. Now you need to remember one important thing, two important thing, that is scalar triple product. What is the scalar triple product? A dot B cross C. Obviously, B cross C is a vector dot with another vector is scalar. See, A, B, C, you can also do C dot A, B, C, C dot A, B, A cross B, or same as the B, B dot C cross A. Same. Like I am following a pattern. I write A, B, C, vector A, B, C. I am following this pattern. A dot B cross C, B dot C cross A, or C dot A cross B. And what is that value? The value is simple in the determinant format. Then vector triple product, that is A cross V cross C, which is decomposed as the B into A dot C minus C into A dot B. That's all. We call it BAC minus CAB rule. Now scalar and vector projection. So let us say this is a vector A and let's say another vector B, and the unit vector along A vector upon magnitude of A, and unit vector along B, AB, let's say AA and AB as the B upon B magnitude. Here two type of projection I'll show. Scalar projection. What is scalar projection? Scalar projection of A along the B. That is the scalar component of A along the B. That means A dot unit vector along B. That will give you the A magnitude and cos of theta. So what will be the vector projection? Vector projection of A along the B is the AB into unit vector along the B. That is magnitude of A cos theta into AB. So normal component of A normal to B. So I have done one here, that is your AB. Then what is here normal component of this? Normal to B, use the relations, vector relations, that is A n V vector is equal to A minus AB. So in a simple graph I'll show you. So I decomposed vector A with respect to B into along, or you can say the parallel and perpendicular components. We'll discuss with an example. What is the vector component along so we know vector component of this. First you find its unit vector. Unit vector of this is the 3 upon 5 ax minus 4 upon 5 ay. Okay, now take the dot product. So 6 into 3 upon 5 minus 2 into 4 upon 5, this into unit vector 3 upon 5 ax minus 4 upon 5 ay. So what is these values? That is the 2 into 3 upon 5 ax minus 4 upon 5 ay. So multiply 2 and you will have 6 upon 5 ax minus 8 upon 5 ay. That is the vector component of this vector along this. We'll do the another example. Vector projection of A along minus ay direction, where A is given by minus 6 ax plus 3 ay plus 2 az. Same rule. Find the, so obviously it is a unit vectors, so find the dot product. When I find the dot product, I got the minus 3. Then along this unit vector minus ay, that is 3ay. That is the vector projection of A along minus ay direction. Then we'll move to the line and surface vector. Line vector, a differential line vector. Let us say this is a line. Okay, so I want to find a line vector. Take very small, okay, differential length dl in a given direction. Let's the direction be the an. So differential line vector is the dl is the magnitude, infinitesimal small magnitude, and the an in the direction, this direction. For example, what is the differential line vector along the x-axis? So dl along the x-axis will be the dx ax, along the y-axis dy ay, similarly along the z-axis dz az. Similarly the surface vector. Let's say this is a big surface, but you need to take the surface. So surface has to be if it is a open surface like circular surface, a plain paper, so you need to have a orientation. So take the small surface in this orientation, let it ds, that surface area. So surface vector, infinitesimal surface vector ds will be the magnitude of that infinitesimal, and an, what is the an? An is the normal to the this vector along. When you curl this in the right hand, okay, so in the right hand curling of fingers, which direction it is, your thumb is showing? In the downward. So this is your an vector. Take the example of, let's say dx, and this is your dy, and the orientation is, let's say this way. So what is the direction of this surface vector? So ds will be the dx dy surface area, infinitesimal small surface. So this will be the an, in which direction? A z. For the closed surface like sphere or cuboid, the surface vectors from this surface, whenever you have an infinitesimal small surface, it will be always outward. That is ds equal to ds an, outward of the surface. For example, this one, let's say infinitesimal small surface here. This is volume. Okay, so you can take, suppose I want to take the surface vector in bottom plane. So obviously this will be, that is dx dy minus az, and if you take this surface, it will be always outward. Surface vector will be always outward. Suppose I want to take for a spherical small surface here, spherical surface, so that will be the r d theta d phi ar, outward in this ar direction. How does it come? It will be discussed later on.